Today we're going to talk about second derivatives of parametric equations. But before we can talk about second derivatives, we have to talk about first derivatives. So, remember parametric equations are defined with x of t and y of t, which you should remember from the last video too. So the derivative of the function x of t is dx dt, and the derivative of y is dy dt. So if we want our first derivative dy dx, we have to take dy dt and divide it by dx dt. And that gives us the first derivative. So the question is, how do we find the second derivative? It'll be easier to see with an example, so we're going to use x equals t cubed and y equals sine of t for this one. So we know the first derivative is the derivative of y, which is cosine of t, over the derivative of x, which is 3t squared. So the second derivative, we just take the derivative of the first derivative, right? Because that's how we do it for rectangular, right? So we do low d high minus high d low over low low. But no, that doesn't give us the second derivative, and here's why. Because when we take the derivative of dy dx, parametrically, we're taking it with respect to t. So really, dy dx, when we take the derivative, it's d dt of dy dx. So that is not the same thing as the second derivative of y of x. So we have to do it a different way. And this is not super obvious, so we'll start, I'll show you what it is and then explain why it's that. So the second derivative of a function y defined in terms of x, really what we want, dy dx, but we want to take the derivative with respect to x, not with respect to t. So we can do this crazy looking thing right here, where we take the derivative of dy dx with respect to t, so d dt of dy dx, which is what we did on the last slide, and then take that and divide it by dx dt, and this is why that works. So if we take this crazy looking thing and we write it differently, this is the numerator, d dt of dy dx, and we multiply it by the reciprocal of the denominator, now our dt's kind of cancel out, so we get d over dx of dy dx, which is what we want because that's what the second derivative is equal to. So this whole slide is just the derivation of what we are doing. In this example, we'll see how we're actually going to use this. So the example, we need to find the second derivative, and usually they'll say something like find the acceleration, and they'll give you the position functions. So anything that you would use a second derivative for, if they tell you to find it and they give you parametric equations, this is how you do it. So they tell us that x is equal to t plus cosine of t and y is equal to sine of t. So I wrote the functions up here, x equals t plus cosine of t and y equals sine of t. And before we find the second derivative, we have to find the first derivative, and that's true regardless of whether this is parametric or not. We can't just guess what the second derivative is. So dy dx is the derivative of y over the derivative of x, which is cosine of t over 1 minus sine of t, and then we're going to do the derivative of dy dx, but with respect to t. So we can do the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, or low d high minus high d low, all over the denominator squared. Now the nice thing about this, when we simplify it, we get negative sine of t plus sine squared t plus cosine squared t, and we remember from pre-calculus that sine squared t plus cosine squared t is just equal to 1. So we can simplify this to 1 minus sine of t over 1 minus sine of t squared, right here. Now we have 1 minus sine of t on the top and on the bottom, so we can cancel one of those out, and we get 1 over 1 minus sine of t. So that is the derivative of my first derivative, but with respect to t, this thing right here. So now we're going to take this 1 over 1 minus sine of t, and right here, and to figure out our second derivative, this is what we're looking for, this is how we do it. We take the derivative that we just found with respect to t, and we put it over dx dt, which was 1 minus sine of t. And now this denominator and this denominator match up to each other, so we can simplify that by saying the whole second derivative, this whole thing right here, is equal to 1 over 1 minus sine of t quantity squared. Here's a problem for you to try. Find the second derivative of the curve that's defined by x equals t cubed minus t and y equals 4 minus t squared. And again, this could be like find the acceleration given these position functions, or find the concavity of the function. So anything that involves a second derivative. But those are your functions. So pause the video here and take a few minutes, work it out, and then when you start the video, we'll look at the solution for this. Alright, at the top we have our functions, x and y. First we find the first derivative, so we have dy dt over dx dt. And then the next thing that we want to do is take the derivative of dy dx, but with respect to t. So you do it like you would just do normal quotient rule. We have low d high minus high d low all over low. And then you can simplify this until you get 6t squared plus 2 over quantity 3t squared minus 1 squared. So now we take this derivative that we just found and put it over the x dt, which is what we have on the bottom, 3t squared minus 1. And this denominator from our previous derivative over our dx dt are the same, so we can combine those, and we get 6t squared plus 2 over the quantity of 3t squared minus 1 cubed. And that is the end of these notes. Remember, if you have questions, ask them. If you're not watching this video at home, write down your questions and ask me the next time you see me.